The second part also is an elaboration on photoelectrochemical hydrogen generation with the specific cases where I have been working on since more than 10 years. And I would be actually giving you some glimpses of that, which will be actually tell you that how important this field and how we people in India can actually work for it to contribute it in that. And I'm coming from ARCI Hyderabad, and it is an autonomous lab of Department of Science and Technology, India. So I hope few of you at least have visited, and in fact, Mr. Rambabu was with me several years ago. And if you are interested in details, you can look at this website. And mainly, this is a kind of lab where in the country where we not only look at the basic research, but we also look at the technology development. So most of the problems or research problems or technology problems, they are associated with technology development, making of the technology, and then giving that technology to industry for usage in strategic application, for usage towards society. And that is main motto in a way you can understand. These are the first areas which give you an overview of the kind of dimensionality we work at ARCI. So it includes the nanomaterials, which is the advanced materials related field all over the world. Then the timely, whatever is important at the present time is automotive energy materials, including the batteries and supercapacitors are another interest. Then solar energy materials. It is again important part of the research all over the world, and a lot of work has been going all over. So that also is carried out at our place. And then we have ceramic processing, which is also an integrated part, which is very much required in present times. Then engineered coatings, which actually includes some kind of different coatings. It can be starting from your aerospace to, it can be hard coatings or functional coatings or sensor related coatings and protective coatings. So that is another part. Mainly, if you look at laser processing of material, which has been frontier topics for peculiarly the ability to process the materials using specific light beam, is of very different interest, not only in material processing, but it has the dimensionality to the communication. And then we have the topic which is very closely related to what I am talking on, fuel cell. Fuel cell needs hydrogen, and then what we are going to look at today is actually the way how to make the hydrogen. So here, as this is a repetition, but then part one, I am going to talk about photocatalytic hydrogen generation. So here you can see that schematic on the top shows that you have a kind of a container or a reactor where you have the photocatalyst suspended in that slurry and an electrolyte, and then you have that, and it has ability to split the water molecule H2O into hydrogen and oxygen. So this is the simple concept of photocatalyst, whereas the photoelectrochemical hydrogen generation as shown in the lower schematic, you can see it is a kind of a film where you have the film of anode type and cathode type, which is actually immersed, the set is immersed in an electrolyte, and under the presence of the sunlight, it is having ability to generate hydrogen and oxygen. So these are the concepts one can take forward to understand while going through the today's this lecture. So as I said, in the first part, actually you have the main thing here is the material development, that is the photocatalyst material. And what is so special of about the photocatalyst? And in today's life, if you are talking about the nanotechnology and nanomaterials, in that scenario, how these photocatalysts are actually modified with respect to the nano-dimensionality, and few examples, those we will see in this part. Now, whenever we ask anybody in today's world, energy is the most important part of our life, which is driving our life anywhere in the world. And then what is important here is when we try to look at what is the energy today we are using and what will be the energy we will be needing, say in 2040, there is a consistent increase in the energy demand. And if you look at the left side, so current global energy use is 16 terawatts, and which is contributed from this where the utilization is in transport sector, then industry sector, and residential and service sectors. Now you understand that if we keep on progressing in this modern life, the energy demand is going to be more and more. And basically, whatever energy we are having today will be, if you can look at the sources of energy, mainly the coal, natural resources, some nuclear energy, and that kind of whatever sources are there, those are actually driving our life. But then the situation will change in decades to come, maybe 20, 30 years. So one has to be under the search of such kind of energy sources which are renewable sources. So this particular slide, you can see that finite energy reserves are there, which will be lasting for maybe few decades. And there are possibilities and some scope for renewable energy sources, and those have very high potential, which we may meet our demands in upcoming. And obviously the bigger circle, the solar energy, is much more than anything else. And that is the whole show, that one can, or one wants to make use of solar energy and renewable energy sources, whatever there are on Earth. So let us see the same thing again. It shows you the arrow wise how we started with using a fuel as a wood, then coal, then petroleum, natural gas, and then we are actually heading towards such kind of energy in the future, which is hydrogen energy. And then it is a kind of analogous example which can be taken from the nature as a photosynthesis. So plants, they make their energy themselves by the process of photosynthesis, and such similar thing can be actually imitated in terms of splitting water molecule and making use of that hydrogen for running our fuel cell and other energy demands. So we actually need something which is renewable source. So if you look at in general, we have a lot of sunlight, we have a lot of water on our earth, they are abundant. So it is always a better idea to go for that kind of technique, that kind of research, technology, where you can make use of the abundant resources in nature, mainly water and sunlight. Now, artificial photosynthesis actually is possible where we turn the hydrogen fuel. If you actually make the hydrogen from sunlight, which is falling water molecule, where H2O molecule can be broken to give you hydrogen and oxygen. And then there is no need to worry about water, which is abundant. And there is no need to worry about the sunlight, which is also abundant. So effectively, the hydrogen economy, which has been we have been talking about for maybe last few decades. There was not much work earlier, but recently, maybe last 15, 20 years, it has started with specific focus is there to develop an economy, which is hydrogen economy. Just for the sake of understanding and enthusiasm, what we may be having among ourselves is what is the today's scenario after so many years of the developments in hydrogen energy technology. So this slide actually shows you that slowly electricity grid and then hydrogen. You can see the right top corner, which shows the schematic where hydrogen actually can be used for power generation, and it can be a substitute to natural gas. You can have a vehicle, then synthetic fuels, then you have biomass, ammonia. Now these things are actually required in industrial and transport sector. And then there are other ways where you can actually make use of this energy, hydrogen energy. And it can come from various ways where non-renewable and renewable. In today's time, most of the energy, whatever hydrogen energy is being generated is from natural resources by ammonia. So this is what we have to keep in mind for our next slide. And then other three examples, what this slide shows that certain places there are the technologies to the end they have been brought, where in Germany the Korodia Island is the train which totally runs on hydrogen. Then Mirai by Toyota actually is the car which totally works on hydrogen fuel. And then Oakland, and there you have the hydrogen fuel which is filled in cylinders, and it is featured in bus, and this bus goes around all over the city. So this is not the limit, but there are few more examples. So what this tells us that it is indeed possible to have hydrogen and expect hydrogen technology in upcoming time. But then what is actually hydrogen, and where is the hurdle that we must understand? So what is important here is to know why hydrogen we are actually focusing on. Obviously, we always compare a particular thing with existing things. So when we say hydrogen is the cleanest sustainable carrier, energy carrier. And it can be useful in a number of ways. But the main thing here is it is no greenhouse gases. At this juncture of time, I also remember that Heatham has green building, and that is what is a kind of scenario is required all over the world. So clean energy is must. So hydrogen is one of the most important fuel talked about, which actually is known for clean energy. Then energy security. Now, whatever present natural resources, reservoirs are there in the Earth's crust, they may be dying off over a period of time. So, with respect to energy security, we must have some substitute. So, here, if you have the hydrogen which is made from renewable sources, that is a kind of energy security for people on Earth. Then you have energy storage capacity of hydrogen. Now, this particular technical point, which is actually telling us that given unit volume of hydrogen and given unit volume of the existing source like gasoline, let us say, there is a tremendous difference between the energy storage capacity. So if you look at the bottom right corner, you have the entire table given that fuel and energy content. So energy content shows that you have this much gigajoule. So if you look at hydrogen, it has actually 10 times more energy content than coal, which is being used present times. So this is the important point again that answers our question why hydrogen. Then end product of hydrogen is water, and which is highly eco-friendly. Again, it comes back to saving our ecosystem. Then it doesn't actually depend on the fossil fuels, and it can be portable. Anyway, these are the not specific points, but top above points are very important to understand. So whenever you think of a car which is driven by hydrogen, it doesn't out very toxic gases and which are actually hampering our planet. So this is the point. The same point I have you can see in terms of this tabular form and this graph or graph, left side and right side. Let's not worry about that now. So in present time, when you look at what are the sources from where we are getting hydrogen and why we are driven to the point like we want to work on making hydrogen by renewable sources. So at present, 80%, 95% of the production, which is mostly used in industries, is coming from steam reforming, that is a natural gas, petroleum products. And then, of course, every technology comes with the efficiency. Those are other points. But let's focus on a particular point like in today's hydrogen utilization in our world, the main hydrogen is coming from steam reforming. Some part is coming from electrolysis, and very minor part, which is still under research, is hopefully coming from photoelectrochemical and photocatalytical process. So if you look at the industries or associated industries, so these are the industries, those produce hydrogen, then via steam reforming, Mahala, UIG, then some other Chinese companies and American company. And in India also, our Indian Oil Corporation, all petroleum industries, they are bound to have this kind of hydrogen generation as a fraction during the fractionation of the natural oil. Then is electrolysis. By electrolysis, these companies, they make hydrogen just to give it for certain particular application in industry. And upcoming, there are only very few industry. Like here, I have stated two, nanotech and sun catalysts. So they actually make some hydrogen generator, and it is a kind of a hybrid hydrogen generator where electric field and photoelectric energy both is used, but then they are still not coming to market for certain reasons, and what those could be certain reasons is clear from our this particular slide. When you look at all these discussions, now you see that the top SMR, cold gasification, electrolysis, they are mature technologies which have been used continuously to fulfill the needs of the hydrogen. And then you have biogasification, biomass gasification, that is also at R&D level. And whatever we are talking about, which is frontiers all over the world in research, is, I can say that early R&D. Then we have to understand, as a person thinking about research or doing certain things in this field, we have to think actually what are the main points there. So there comes, like any technology is actually judged by its efficiency and cost. So at present, if you talk about, if you try to estimate what is the cost of hydrogen, 1 kg of hydrogen generated, you're using your PEC, say, then it comes to $20 per kg, and which is not actually very attractive, because one needs to have a price which can at least compete with the existing cost, that is $1 or $2 per kg. So efficiency and cost, these are the two things. And here is what we people who are actually enthusiastic about various type of research, technology development, material science, and kind of engineering of the new materials, we have to come in this particular part. So material science has a lot to do, and a lot of scope is there to design new photocatalysts and to fabricate the reactors which will be useful for sustainable hydrogen generation from these type of materials. So let us look at that, what exactly happens when you talk about generation of hydrogen by splitting of water. So this is especially the case of photocatalyst, where, just one second. Okay, so sorry for the interruption. So here what I'm showing in the slide is a principle of how a photocatalyst splits water molecule to generate hydrogen. And it is very simple school level equation which anybody knows. But then what are the kinetics, thermodynamics, chemistry, physics, material science, optics, and electrical properties, those are involved in this, is a kind of a very challenging job to make a perfect, well-suited photocatalyst which will work under sunlight continuously to break water molecule. Now let us look at the chemistry behind that. Is when you look at the schematic of right side, where it represents a photocatalyst as a suppose single particle, and you can see a particle of some semiconductor which shows valence band here and conduction band. So any semiconductor which has which is known to have valence band and conduction band, where band gap is also known. And if that band gap is enough, that one can use suitable radiation to excite the electron from valence band to conduction band. So this is a kind of picture a simple photocatalyst can be visualized upon. Now here what happens is you can see CAT1 at the left top corner of this schematic and CAT2. So catalytic reaction 1, catalytic reaction 2. What happens is you have two reactions going on here when you actually try to break water molecule. So at valence band, what happens? You have the oxidation, and at conduction band, you have reduction. So if you look at this reaction, you have hydrogen ion plus E, which gives you H, and then such two H active hydrogens combine together to give you hydrogen at your conduction band. So catalytic site 1 and catalytic reaction 2, that is near valence band, you have oxidation, which actually gives you the oxygen. So if you look at the chemistry behind this using this reaction, so you will understand, you will make out that final outcome from this is oxygen. Now, effectively, overall water splitting can be put in this term, like H2O can give you H2 plus half O2. And then how it happens thermodynamically is there's an energy of 1.2 electron volts required for this water molecule to break and give us the water splitted in form of hydrogen and oxygen. Now this is a very challenging job because you're doing everything against the nature, and then natural bond of water you want to break, and that whole exercise is a big challenge. And what is the criteria to make photocatalysis? So this is a chemistry part of it. Then let us talk about, as I already told you, a semiconductor. Semiconductor has certain band gap and it has certain valence band and conduction band edge. So main thing here is when you're talking about the breaking of water molecule, then you must have a band gap which is lying in 1.6 to 1.8 if you want to do this using sunlight. So this will be clear from, again, next schematic. So here what I want to drag your attention towards this particular potential vertical line. You have this particular level 0 and 1.2. So this is the reduction level of water and this is oxidation level of water, and this is regarding your water molecule. And then this side you have the photocatalyst with specific valence band and which is at particular energy level, and conduction band which is at particular energy level. Now how it suits to the oxidation and reduction of water molecule is actually relying on this particular picture. So which will be more clear in our next slide. So here effectively what we have to understand that to excite electron from valence band to conduction band, if you use sunlight, then this band gap has to be within that range where sunlight actually can excite, do that job. And then these levels of valence band and this oxidation potential of water, and on second hand, like you have conduction band and this reduction level of water, they have certain energetics to play. So that is what I showed in the last slide, that photocatalyst can be used for complete water splitting. But then nature doesn't give you so much of freedom that you very easily can do it using one particular photocatalyst. So other way around, there is a scope for doing the same thing. Separately, you have the photocatalyst which can only view hydrogen, and where you can actually execute reduction of water, like here what I have shown in left side. And then you have a photocatalyst which totally works for photo oxidation of water. And then in such a way you get from two type of this photocatalyst, the oxygen and hydrogen. So this is another way to do it, but then the things are not very straightforward. So as we were discussing, our designing of photocatalyst is very stringent and very complex and a big challenge, which is bound by several material property requirements. So there is a lot of physics, chemistry, and all sort of areas are involved. And in this interdisciplinary work, you cannot actually, you need to have all the things together. So how you design efficient photocatalyst, where you have to take care of structural properties, optical properties, electrical properties, chemical properties. So this is the schematic which tells you that material has to have particular band gap, particular energetics. Energetics means whenever you have a semiconductor with a specific valence band and conduction band level, and when it is immersed in a particular electrolyte, how those levels are affected and whether they are really able to execute the respective reduction or oxidation reaction. And then apart from that, the chemical stability of these photocatalysts is another important point. So whenever we talk about these aspects, we must have also very high crystallinity of this photocatalyst. Then there's electrical conductivity, electron and hole transfer related to that photocatalytic reaction. And that will be clear from our next slide, where I will explain you in upcoming slide. Now, as we said, optical properties are important. So our material has to have an optical property like the band gap, which should lie in, let us say here, in the energy which is coming up from sunlight. Especially we are interested in visible light, making use of visible light. So when you look at the visible light, mostly this particular range of 2 electron volt would be worth enough to actually use for this particular work. In past, there was a Nobel Prize for TiO2 for photoelectrochemical water splitting, but then TiO2 is having a band gap of 3.2 electron volts. And then from sunlight, you cannot expect that UV, which is included in our solar spectrum, would be useful for breaking the water molecule in the presence of TiO2 as a photocatalyst. So whole world is looking at something of lower band gap, which can be used for photocatalyst application. So what we want is low band gap material. Then we have the material. Mostly these materials are put in some electrolyte at particular pH. So what happens that with time, the reactions are going on, they may fade away, and then you may see that there is some kind of corrosion or some kind of change in the phase of the photocatalyst. So these things tell us that the material what we are going to use as a photocatalyst has to be stable in light. So as far as the requirement is concerned, the first thing is we must have a material with the band gap which lies within the range what I have mentioned here, which suits to our visible light coming from sunlight. Then band gap, band edge positions. So band edge positions, the conduction band and valence band edge has to be straddling the redox levels of water. That will be clear in our this particular graph. I will tell you about that also. So about band gap, band edge position. Then stability. And stability, as I already told you, about the stability of a photocatalyst with respect to the pH, and then cost effectiveness, abundance, and processability, of course, comes everywhere. Now, what I was saying that this particular schematic where you have this dotted level, dotted lines, which actually tell you that this top one is reduction level of water and this bottom one is oxidation potential of water. When you have this put in the scale and then you put the valence band and conduction band level and you draw it over this, because what is the main point here is your normal hydrogen energy, that is level thermodynamically, how this conduction band of, let us say, TiO2 and valence band of TiO2 fits here is the main criteria for suitable band energetics of the photocatalyst. So those who have basic knowledge or who are interested in solid state physics, understanding of semiconductor physics, and some kind of thermodynamics, we need to know that to understand that this particular aspect, and hopefully everyone must be teaching these things to the students. So coming back to this point, like this other example, I'm just showing TiO2 is this one, and then you have another example of Sirius. So you see these two systems, let us talk about only two systems at this moment. These two systems, they straddle this particular dotted line, and this is the requirement to have a suitable band energetics of photocatalyst, and that makes a photocatalyst suitable for the water splitting. Now you may also see that, let us look at a case of iron oxide where this conduction band is not crossing this level, but it is under that reduction potential, whereas the valence band is much below the oxidation potential. This is the oxidation potential of water. So here this is suitable for your photo oxidation of water. And on the contrary, if you talk about something like silicon, so this is the silicon. So when you look at silicon, the conduction band is much above your reduction potential of water, but the valence band is not actually straddling this particular oxidation potential, but it lies in between. So this kind of picture tells us that it can be useful for application in reduction only, and this is the criteria we have to make and explore for each kind of material we look at. Now if you go by line on line, like strontium titanate has similar picture, then iron titanate has a picture where you can use it only for oxidation. So similarly, barium titanate, it can be used for total water splitting. But you see, these, even they are able to break water molecule, but the band gap is very large. So 3.2, let us say TiO2, 3.2, if you want to excite electron from this valence band to conduction band, you need to eliminate, or you want to irradiate by a photon which has 3.2 electron volts and which actually lies in UV range, and that's make the life complicated. Whereas what we need today's time, we directly want sunlight to do this task, not UV, and that is the reason what we want is we want something like 2.5 or maybe 1.7 or in that range, some photocatalyst which can straddle this whole redox level of water, and then in that way it can be suited. Okay, well, I hope we are understanding and going synchronization with what I am explaining. Now let us look at this particular point. Here in this table, what we should look at is the band gap of the material and the stability, because this stability is meant to tell us the point, like what is the challenge in nature. Nature has given us few of the systems which are perfect with respect to the band gap, but not with respect to stability. Whereas that is the case which is found in serious cadmium sulfide, cadmium selenide, telluride. So these systems, they have very suitable band gap, which can be make it suitable for using sunlight, water splitting by sunlight. But if you try to implement this, then it takes no time to degrade these photocatalysts. So that is a challenge. On the contrary, if you talk about TiO2, very stable photocatalyst, and if you look at the band gap, it is very large. So sunlight cannot break this. Sunlight cannot be useful here, but you need to have UV light to do this job, and which is practically not required for us. So then, if it is something what we have to talk about, like what can be appropriate among existing materials, then serious, okay, unstable is there, but you need to work on to make it stable. Then maybe TiO2, how you can make it to convert it or tune its band gap, that is one scope. But look at this iron oxide and tungsten trioxide. Here they have very good band gap, but then what we see, the efficiency of what? Efficiency of making hydrogen, like solar to hydrogen. Like you put one photon on this material and you get one water molecule broken to give you hydrogen. So that kind of efficiency we are looking at. So solar to hydrogen conversion, that efficiency is very low. So effectively what we learned here is we have to be very careful when we design a photocatalyst, and then design should be such that it should fulfill all these parameters like band gap, band edge positions, stability, and then cost effectiveness, of course, comes with every technology. Now, after discussing all these materials in this slide, what, as I already told you, is CDS is an ideal system, but then it suffers by the instability. So it is a challenging job for us, but then advancement in processing technologies, advancement in the characterization technologies, and then refinement in the way we can actually tune the material properties. It has given us a lot of options to make the material of our interest. So I'm just giving one possible way here, that what can be the different options. So you can see first option to fifth option. First option is you try to make something single phase material, which is new material, and that is one possibility. So people in our faculty, they must be having different experience, and some of you may be actually having a small experimental lab. Some of you must be having some computer based background where you may be doing some computational thing. So if I want to tell you that we have to work on new single phase material, then people from computational background can come forward and they try to simulate the electronic structure of new kind of material, and which can be actually taken forward based on their final expected results, and those new systems can be experimentally attempted to make. So that is one possibility. because in colleges, infrastructure wise, there are limitations. The computational wise, if you have a table and a computer of suitable speed and your interest and enthusiasm, of course, so you can actually do that kind of work there on the table itself. Now, this is a possibility, but this possibility can be extended to any kind of designing of photocatalyst, not only new material, but other things also that you will see in next slide. So let us push on to next one, like photosensitization. Like TiO2, if it is doped with certain kind of dopant, then there is a possibility that you can actually tune in its optical property. I, I understand this is these terminologies are people are well versed with these terminologies because we have been through that learning process of physics, chemistry, engineering, materials engineering. So what is the main point here is you actually try to tune the band gap or the optical absorption. Let us say in this particular case of TiO2, you have TiO2 which is 3.2 electron volt band gap, which is very large band gap. So if you if you sensitize with certain impurity, then there is a scope that this TiO2 can absorb the visible light radiation. So atoms also are going on with different kind of dye molecules, but then there is always a limitation to every dimension as you go on working. Then third possibility is modification of the whole system, like your crystal structure. If you have a particular kind of let us say oxide and you turn it to let us say sulfide. I'm just giving you an example. It need not be sulfide because maybe we need to answer this particular thing with some stable material. So for just an example, if you have a crystal lattice where it is oxide based and you substitute oxygen with the sulfur and or other impurity and then tune in the band gap with a new or different kind of its converted material. So this is the modification of your optical absorption from this high band gap to low band gap. This is actually for if you understand this or you have to recall that this is the optical absorption spectrum where you have wavelength on x-axis and absorption on y-axis. So suppose you have silicon and material and you take the optical absorption spectrum, so you may get something band edge at 1.2 electron volt, which can be converted to your nanometers. Whereas you take the TiO2, for example, and it may have higher absorption edge at lower wavelength. That is the indication of this particular graph. Then let us talk about the composite photocatalyst. Composite photocatalyst is something where you have the two type of different photocatalysts, let us say TiO2 and CDS combined together. So it is a kind of a composite photocatalyst. Or by definition also, if you have something different in mind, like you just substitute a particular species of atom in a particular system of photocatalyst and combine it with some other second photocatalyst. So this kind of composite photocatalyst engineering can be done. Just 1 second. So that is a possibility. So what is the use of this? Actually, we are tuning electrical and optical properties so that we can actually get suitable photocatalyst. So something similar you come up with, like wide band gap material and narrow band gap material. You totally convert it in such a way that it gives you a solid solution of new kind. So that is a possibility. Let us not discuss more on that now. Already we spent a lot in that because that is the basis of our whole discussion in upcoming slides. So theoretically, how physics can be used is what I just gave you a few words during last slide. Like strategy to face this challenge of making a new material or a material which is having suitable optoelectronic properties. So theory, then modeling, then experimentation, and then technology. This is a kind of cycle we need, if at all we have to do a very challenging job. So density functional theory helps in this. Now here what you see is the band structure of a particular material that can be simulated. Then you have optical absorption spectra of a particular material that also can be simulated. And based on that knowledge, you get that from your theory and modeling. So those results you can actually couple with your experimental whatever measurements. Now here I am actually only user of the computational code. So we just have to think of this particular thing where you try to solve a Schrodinger's equation quantum mechanically, and that basis is here where this particular calculation of electronic structure can be exploited for calculation of electronic and optical structure of a particular material. So I am not going to make any code, but these codes are existing, like Win code is there, WASP code is there, and then number of other codes. Those can be taken by you, those who are actually interested in such kind of work, and they can start working on not only this, but there are several other dimensions. And people having exposure to this, or people start taking interest in this, will find several dimensions, not only in the material science, but DNA or some bio-related aspects also. Now, this is what I had to tell you to educate ourselves, to understand what exactly we are doing and how we are doing and what we are doing. This is the number of photocatalysts which we actually tried in past and till latest time. So in general, you talk about ferrites, niobides, titanates, then 2,6 chalcogenides, then nanocomposites. So these all different systems we worked on. Mr. Rambabu was also with me for particular aspect of CDS based work in past. So what here we have done, like these whatever oxides or ferrites, niobides, titanates, they are important and one needs to work them for improvement in the efficiency. Whereas the chalcogenides, there one needs to work in controlling the stability. And some nanocomposites where both improvement is possible. Improvement in your stability as well as efficiency. And to some extent, if we want to get rid of number of experimentations, and if it is really possible, then it is left side, you can see theory, modeling, and technology. So again, that remains the same point, like to make something new or to understand the band energetics, the band gap, or whether it is going to work for this particular type of photocatalyst application is actually very important. And if you are not of the opinion that you should do hundreds of experiments, then one can always look at computation and then implement that and try to attend those selected cases for experimental validation. Now, whatever things we discussed in the past slide, that comes as a basic understanding about the mechanism, then material science, and whatever physics, chemistry, or whatever is involved in that. How to do that and what are the things required is the point what we see in this slide. So when you want to eliminate your photocatalyst, you should be able to tuning the photon wavelength, let us say from 200 nanometers to, let us say, 1000 nanometers. How to do it? That can be done using your monochromator. Then if you have a specific sunlight type of simulation, sunlight type of radiation, like we want to make use of sunlight, solar radiation. So we actually have a solar simulator which can simulate the radiation, and it gives us that particular radiation which we can actually find at particular location on the earth. So there are some filters related to that. And then you can also tune it to 1 sun, 2 sun, and then different AM related radiation. So those are the things that also you need. Then once you have, and you want to confirm whether your system is generating hydrogen or oxygen, for that you need the gas chromatography at least. So this is the kind of setup which we actually need to use. So conceptually, if you see that this particular thing, you have a catalytic, photocatalytic slurry kind of mixture in this. It is eliminate radiation, and then this is connected to your GC, and that is the way it is done. So photocatalyst material. Now I am just showing you a few cases where we have actually made use of the ideas what I have discussed, and we find out. So we have to identify material of interest. So we have to find out the physical and chemical properties, compute the electronic structure, optical structure, and then correlate with the experimental properties, and then experimental validation of the photocatalytic properties. So this is the study where what I am trying to show here, and in this slide quickly tells you that barium stannate BaSnO3. BaSnO3 is a material which has large band gap of 3.2 electron volts. Now, our hypothesis and our idea was, if we select this kind of material and then we go on doping, say different dopants like titanium at SN site, or vanadium, or chromium, or zirconium, or lead, or like this, then how the optical property, electronic band structure is affected, and how that can be exploited for designing of a photocatalyst. Now, this particular thing left hand side, you can see it is a graph of electronic structure which is simulated from the software. Now, on right side, you see this is the same graph where we have the redox level of water molecule and these conduction band and valence band of each of the system like TiO2, barium titanate, and then dope systems of these metal ions are actually drawn on this particular graph. This tells us that what are the possibilities with respect to the particular type of material and its suitability for the photocatalytic application. The TiO2, as I said, is a standard material and has a band gap also very large. Barium tin oxide, again, there are certain limitations with respect to your softwares sometimes, and then the functionality of the software is also a kind of a based on assumptions which is related to the final outcome. But then nonetheless, if we know a particular drawback, based on that also, if we relatively look at the computational result, what we see here, when you dope titanium, when you dope vanadium, when you dope chromium, zirconium, these are the possibilities which shows that zirconium doped one can be used, but then can be used as a photocatalyst, but then its band gap is too large, more than 4. It is not actually good idea. Then in any of the cases like vanadium dope, it tells us that it can be good for hydrogen evolution, whereas these other ones can be useful for your oxidation reaction. So what we see here is actually that one can make use of a particular type of photocatalyst for a particular photo oxidation or photo reduction. Now this is all, this left side and this particular thing is computational result. Now we selected one system like lead doped tin oxide, barium tin oxide, and then we attempted experimental validation, and you can see that at particular stoichiometry, at particular type of level, it shows very good efficiency of oxygen evolution, because it is good for oxygen evolution. So this is the type we have validated, that how one can design and make a visible active photocatalyst. Same thing we did for the second case of strontium titanate. Let us not worry about that. And similar things I have this for lead bismuth niobate, where you made use of this electronic structure calculation to interpret the high efficiency of lead bismuth niobate photocatalyst, which works very well in visible light. So these are the different systems we worked on and published. But then ultimately this tabulation tells you that titanium oxynitride, where I was telling you that you can tune the absorption property of TiO2 by doping of, let us say, nitrogen, it is compared with lead bismuth niobate. So you see efficiency of hydrogen evolution and oxygen evolution of lead bismuth niobate is very high under visible light as compared to titanium oxynitride. So this tells us that just doping is not a good way to do that, and lead bismuth niobate indeed was a good system. Then as time evolves, no, there are the possibilities that one can get various new systems. We can design new systems to get highly efficient photocatalyst. This is a work where we our main intention was to look at the economic material, and which is eco-friendly. So ferrites, which we studied, and here again we have made the ferrite photocatalyst quickly in 10 minutes by microwave sintering, and this is the specialty of this work. And simulation, electronic structure simulation also is correlated with this particular material for photocatalyst application. So this slide shows that zinc ferrite and magnesium ferrite are very good and for our oxygen revolution, whereas calcium ferrite gives very good catalyst as a photocatalyst as hydrogen evolution. Now I think this part I will not talk because it is the same part. Only I have number of papers cited in that. This part is more important for us. So I think we have some 15-20 minutes. So photoelectrochemical configuration. Now whatever upcoming things are there, they are more getting focused towards the photoelectrochemical hydrogen generation. Why is it so, and what are the typical differences and peculiarities with respect to photocatalysis? So as I already told you, here you have a film which is coated with the photoactive material for anode, photoanode, and as a photocathode, or just photoanode and a standard cathode of platinum, or vice versa. Like you have anode as a metallic standard metal electrode and photoactive material coated for cathode. Now, this slide is just introduction. Now, what is the important thing I want to show you here is this is a bit different than our photocatalyst. In photocatalyst, you use only photons to execute the reaction, whereas in this particular case, you have additional electrical biasing to the set of what? This is what left hand side shows as a photoanode, what we make based on our designing of the material, and this is on the right side counter electrode. Now this whole set is having certain biasing and it is immersed in the electrolyte. So band energetics you can see here. So what happens is this hole is actually giving you the oxygen, and the same thing you see here. How this hole is generated? By elimination of this particular photoanode using sunlight, and then you get the exciton pair, electron and hole. So electron is actually going to this counter electrode, and here you get hydrogen. So same thing, you have oxygen here and hydrogen here. So this is photoelectrochemical cell, and this is the principle it works on. So our main point here is to work on the part of photoanode material. So which is the best photoanode material and how it suits to this application. So it comes to the same criteria what we told, but here additional things are there, like this has to be in the form of film, and then electrical properties of the materials are equally important, where you can actually have an idea about the electron and hole mobility. So what I was saying, so development of electrocatalytic material that is in form of film is main issue. And then what we want, focus is something like you must have something of particular this type, where you have a membrane based electrolyzer where you generate hydrogen and oxygen under the sunlight. So maybe you can see black box. So this black box can be of this sort, and then sort means not exactly. I will show you that here. Like here, if you have this whole reactor which is having the coating like this on it, and it is connected to certain biasing under the sunlight, and you have continuous flow of electrolyte, then it should generate hydrogen and oxygen. So that has been that is being going on all over, but there are a number of problems, chemical engineering problems, aspects, reactor designing aspects, then sustainable generation is hampered by that. So what is important here I want to tell you is just like a particular technology which is worth or not, and what is the driving force here is we have to work on making a photocatalyst or photoactive material for this PEC, which can be having very good optical absorption, and when it is used stably in electrolyte, it should give you the STH of 10 to 25 for 1000 hours of continuous running, so that we also have the cost of 2 to 4 kgs per $2 to $4 per kg of hydrogen. So the aspect remains same, that efficiency improvement and improvement of stability. Here additional thing is like electrical field. You have a biasing. So you need a biasing from electrochemical workstation. So that is additional thing which is required. And then this schematic shows you that you have a working electrode which is made by our work, and then we have the counter electrode. Counter electrode, mostly if it is a single electrode configuration, then counter electrode is platinum. So this kind of setup is used for characterization. Now I am just giving you some case studies, because I told that we always need to look at eco-friendly materials. So here also we attempted the ferrite-based thin film, and then we have actually shown the uh, performance of hydrogen generation, and it is generally a challenging thing, but very good film and with sufficient efficiency. So something similar you have. Okay, this is, I can skip. Just 1 second. So sorry. So this is the main criteria which controls the parameters related to photoelectrode fabrication. So what is here is we should have a narrow bandgap material, and then which should have a proper reflection layer which make it stable, and then certain other parameters which are important for this particular work. They may not be of more interest at this moment to uh, general audience. So charge separation efficiency, charge transport efficiency, and charge collection efficiency, all these things are very important for making a good efficient photoelectrode. Yeah, so what I want to show you here is using iron oxide, eco-friendly material, we tuned the iron oxide nanoparticle size from 5 to 16 nanometer and made uniform particles, and using those particles we made a film, and then we looked at the solar to hydrogen efficiency, and that is the point which is very important for basic understanding that with respect to nanostructuring whether there is a change in the solar to hydrogen efficiency. So this is what we have published in Applied Physics Letter long back, and what it is, if you have a particular size of particle of iron oxide, then it has more so S to H ratio. So that is what we can see. 12 nanometer size is the most suitable in this study. So same thing actually here, I'm skipping that. So we have made use of CDS to so here you can see we have made a very large area CDS electrode with a nanostructured film, and anyway this work we have already published in different journals. So CDS as it is, when you do make use of CDS electrode, then its uh, stability is questionable, is as shown in the particular graph. Now, what happens if you look at the basic mechanism of instability or stability of CDS, that occurs due to photocorrosion. And then to arrest the photocorrosion, we actually thought of making use of a criteria of nanofunctionalization. CDS. So using this particular aspect, we have in ARCI we have worked on modifying the series electrode to make stable and efficient series electrode. So we tried nano systems of TiO2 niobate systems and MOS2 nanoparticles, nickel oxide nanoparticles for functionalization of series particles, series based photoelectrodes. And then it was very interesting to see that nano TiO2 based functionalization gave us very suitable, stable and sustainable hydrogen generation. So this is the important outcome. So how this has happened? Just by our basic understanding and material science engineering. So I think these things, second system, niobium oxide, we tried, and that is what we can see the stability. It has also shown very good stability. This particular MOS2 based system was very efficient, and this is the way we were able to tune the morphology of the MOS2 based nanosheets, and which are used for functionalization of series electrode, and it gave very wonderful efficient electrodes for hydrogen generation. In these results, you will also find that we are showing hydrogen efficiency improvement, but I am not explaining that. But it is clear from this particular table from right hand side that the series which is modified with nickel oxide gave very high efficiency of hydrogen evolution in a PEC reactor. So basically, such stability is acquired by a nickel oxide based modification, and it gave us the STH of greater than 3%. Now, using simple system, you can not reach very high values of STH, but then there are certain systems like gallium arsenide, gallium phosphide. They are very unstable, but they can give us the efficiency of STH more than 14%, 20%. And on the other hand, there are some very expensive noble materials. If they are used, then they also gave more than 25% of STH. But commercially, their feasibility is always a questionable. So we have worked for making some eco-friendly and economic ways of designing and fabrication of photoelectrode. So what I want to say finally that for everyone, we have a lot of scope in development of these photo anode or photo active materials of specific category, and then we can make use of our expertise and reach respectively to a stable, efficient photoelectrode for reaching the goal of producing hydrogen energy of very low cost, which actually target is for whole world to make hydrogen of 1 kg within the range of $1 to $2 cost. So if that is done, then maybe we can have a lot of scope in giving this hydrogen technology to world soon, have enjoying clean air everywhere and clean water, and those are the ways we can drive our future towards a better life. And then I want to acknowledge all those who support this work, and also from Korea also I have some collaborators, and then with whom so I worked, and I think that is the end of this. So hopefully I skipped few slides for the reason that the time was, and it was a kind of a repetition. Thank you.
Thank you very much, sir.
Yeah, I am not able to see actually.
Thank you very much, sir. Really, it's a wonderful session.
Yeah, thank you. I have taken a lot of time or what?
No, sir, on time. You strictly maintain the time.
Yeah.
Now it's open for discussion. The participants are requested to ask the questions.
Good afternoon, sir.
Good afternoon, sir.
This is regarding hydrogen-powered vehicle and photovoltaic powered vehicle.
Okay.
In both the cases, which is more energy efficient?
This is at this time when the technology of hydrogen is not very matured. Uh, Maybe we will have to judge on the basis of the aspect like what is the cost involved in making this technology. So what I say at this moment, if we are able to reach maybe more than 7% STH, then hydrogen production cost will be low, so it can be promoted. As far as your question with car driven by gasoline and
Photovoltaic cells.
photovoltaic cells,
Yeah.
okay, and hydrogen based, huh?
Yes, sir.
Okay, so which is good? That is the question.
Yeah.
Now, if you talk about this hydrogen car Mirai, which has several stacks of those are made from by making use of platinum based material, and its cost is very high. But then particularly if you look at the driving and its usability, then uh, it has a more advantage. Whereas PV, photovoltaic based cars, uh, they will highly rely on the they are being used. So assuming that they are in area where you have a lot of sunlight, then still there will be a restricted application in certain areas only, like short term or radiation based. You have a lot of exposure of sun. Those places, I think it is useful. Technology wise, solar PV will have its own advantage with respect to cost, but then best technology or performance wise, hydrogen technology will have its own benefit. So clearly it is difficult to distinguish and tell exactly, because PV also is a kind of a technology where you cannot fit the solar panel to your car and then it works well. There also you need something to store. And similarly, when you have hydrogen based, there also you have to make use of the hydrogen which is already generated and fill in the hydrogen cylinders and fit it with your fuel cell car. So what I think is, in either way, if you look at rechargeable or storage mechanism is also important point which will drive this technology, whether it is PV based car or hydrogen fuel cell based car.
Sir, what I feel in
Yeah.
a dynamic systems, it is more preferable for photovoltaic mode. In a static energy generation, the hydrogen based systems may be suitable. Am I correct in that my approach?
That is what in dynamic system also, when you have the uniform solar radiation throughout the region, like you have, what I understand, your rooftop is made up of the photovoltaic panel. Am I correct?
Yes, sir.
So if that is the case, and provided your efficiency of conversion and the solar light radiation is ideal, then maybe if it is in real time, there also you need some storage mechanism which will drive your vehicle. So in a way, if you purely categorize about dynamic and stationary, then even for your solar based thing or hydrogen PEC, photoelectrochemical based hydrogen generation, the stationary would be preferred. Whereas we talk about PEC, photoelectrochemical with your car, then that is obviously a difficult thing.
Okay, thank you,
As
sir.
you said also. Thank you.
Sir, there is one question from Dr. Madhusudan Rao. Could you please suggest some useful DFT freeware?
Freeware is, I think, number of Abinit is there, and in fact they have a set of softwares which are freely available, and there is on that website of maybe your computational codes for DFT. If you find out, I find a dozen of them, but it is difficult to name them. In case he wants specific information, I can share that by mail also. But what I suggest is Win is a good software, Win 2K, and it is hardly, I think, 500, maybe $500. So, but that is a licensed version. It has more functionalities, and hopefully that would be more appropriate. Otherwise, he can contact and I share that. Dr. Madhusudan Rao.
Any more from the participants?
Sir, good afternoon, sir.
Yeah, good afternoon.
Hello.
Yeah.
Sir, very nice presentation, sir. And one question I want to ask, sir, that is, what is the use of what is the advantage of nanomaterials compared to bulk materials in order to produce the hydrogen?
Okay.
You have suggested both the things, sir. But what is the advantage of nanomaterials compared to the bulk materials?
Everything, whatever comes with nano, specifically for PEC hydrogen, it comes with added efficiency because of its surface dominating effects, and in some cases the electronic structure based modulation also adds to improvement in the PEC hydrogen generation. Similar thing is not exactly true for this. It is only beneficial mainly for PEC. When you come to photocatalyst, then your host, main host photocatalyst has to be of very high crystallinity, and there you can actually think of modifying it with some nano-based material. So this is what I think I have answered you.
Yes, sir. Thank you, sir.
Thank you.
Any more questions? I think there are no more questions from the participants.
Yeah.
Okay. Thank you very much, sir, Dr. P.H. Borse. We are extremely thankful to you for having accepted our invitation as a resource person to deliver lecture in our faculty development program on recent trends in material science and technology. We are extremely grateful to you for sparing your valuable time and enlightening us with your interesting and informative lecture on the topic solar hydrogen material. I hope the participants would be hugely benefited by it. And please accept our deep sense of gratitude on behalf of Hyderabad Institute of Technology and Management. We hope one day we will produce very low cost, eco-friendly and highly efficient hydrogen generators. Thank you very much for your valuable presentation, sir.
Thank you, sir. Thank you very much.
Really wonderful and very informative.
I hope I have fulfilled And
Yeah, really, sir. You covered right from the basics to the recent trends. You have made 100% justice to the title of this program.
yeah, so then I'm
We
happy.
are enlightened.
Yeah.
Yeah.
Thank you very much.
Please, sir. You want to say, you are saying something. It seems I disturbed you.
No, actually that's the same thing. My main purpose was to create more enthusiasm and give some kind of ideas to promote
Yes,
this
sir.
work at your institute, so that even computational wise or experimental wise, whatever way they are able to put
Yes, sir.
their knowledge, their
Yes, sir.
efforts to do
Yes, sir.
something, that will be very good
Yes, sir.
outcome from this talk.
Yeah,
That is what,
your entire presentation was very much informative and inspirational also as well.
yeah.
Really. Your hard work, commitment, everything is reflected in your presentation. It's
Yeah.
a great pleasure to have you today.
Thank you very much, sir.
Yes. And we look forward similar cooperation and enthusiastic participation from you in future, sir.
Yes, sir. I'm
Anytime.
always there for benefit of all our future generations. And please let me know.
Definitely, sir.
Yeah. Okay, sir.
Okay,
Think
sir.
I can stop
We
the
can,
video
yeah.
now, or
Right, sir. So with this, I am concluding this session.
sure. Okay, sir. Fine.
Okay, sir. Thank you very much.
Thank you very much.
Thank you, sir. Thank you, sir.
Thank you,
Professor
Ram.
Rama here.
Thank you.
Thank you.